I'm sure you're familiar with the math YouTube channel Flammable Maths run by Jens Lau. He makes awesome math videos that have some humor in it. Today, him and I are going to be talking about variational calculus and the Euler-Lagrange equation. So the idea for variational calculus stems from a concept you've learned in single variable calculus, local minima and maxima. Let's consider a function f of x. We know that if we want to find the local minima and maxima of this function, we just take the derivative of the function and set it equal to 0. But finding these points where the derivative is equal to 0 doesn't tell us if it's a local minimum or maximum. It simply told us that the function was stationary at that point. To find out if we're dealing with a local minimum or maximum, we would do further testing, using the second derivative test for example. So the idea for a stationary point for a function was just to define when the derivative of the function is equal to 0. But what if we're dealing with functionals? A functional is a function of functions. It's just a function that takes a function as an input. A classic example is the distance functional. Let's consider 2 points A and B. The distance functional takes some function f and outputs the distance from A to B along that function f. Variational calculus deals with finding stationary points of these functionals. Notice the difference. In the traditional calculus case, we have a function that maps from real to real. But in the variational calculus case, we have a function that maps from function to real. In both cases, we're finding stationary states of the function, but traditional calculus tries to find the stationary point, where variational calculus tries to find a stationary function. Let's consider the distance example again. Given 2 points A and B, the distance functional takes in some function f, and outputs the distance along that function between A and B. Now the goal is to minimize this distance functional. Now obviously the function that minimizes this distance functional is a straight line. But let's look at what this distance functional would look like. Considering points A and B have x coordinates x1 and x2, the distance functional can be written as the arc length from x1 to x2 along f. Using the formula of arc length from calculus 2, we can write this distance functional. And if we reframe the problem, we can say that the goal is to find some function f that minimizes this integral. This example can get more and more complicated. What if as we move along the path, we are obstructed by friction that changes the velocity? What if there's gravity? In the case of gravity, this problem has a special name, the Brachistochrone problem. You might have seen videos by Vsauce or 3Blue1Brown on this topic. A more general way to write the problem variational calculus is trying to solve is to find some function f such that the integral from x1 to x2 of capital F of x, f of x, f prime of x is a stationary point. Notice the integrand has a function that takes f prime of x as an input. This is something we did in the distance functional too. This function capital F is called the Lagrangian. Now you may ask, how do we solve this question? I'm going to pass it back to Papa Flammy to derive the Euler-Lagrange equation, the key differential equation to variational calculus.
Good morning! Mein Name ist Papa Flammy. If you don't know me, link probably down there in the description. If you know me, hello from the Papa to everyone out there. Thanks to vcubingx for having me here on this show. He already did a little introductory part for the calculus of variations, and now we would like to derive basically one of the most important parts of differential equations there is in mathematics and also physics. It has a lot of applications in physics. So at first I would like to start off by telling you what this right here is. This is what we had before, where vcubingx used capital F here, and instead of q he used, for example, x. So I'm using filthy physicist notation. Those are our constraints basically. T is just the time and q dot is the time derivative of q. Now with that out of the way, we would like to take a look at optimization, at minimizing a problem, for example. We're going to take a look at a certain curve at first. So let's say it goes from two nodes, so t1 to t2, and this is our curve, for example. Now, let us say that this curve is already optimized, okay? So meaning q in here is going to minimize our function in some way. Now we would like to add a little bit of noise to this function. We would like to put a little bit of error in. Meaning, let's say, for example, we are going to choose nearly the same curve. It's just a bit stretched outwards, for example. Now, we would like to describe this new path of this curve. We are going to do a little transformation. Our original q, okay, it's the function between those two nodes, t1 and t2, is going to be transformed into, we're going to have our original path, q, yet again, plus this arrow term that we are going to have. We're going to give it a certain notation. We are going to give it a certain degree of variation. It's just a real number, could also be 0. Okay, let's call it s, that's the degree of variation. And we would also like to put a little function on there, because you can only add functions of x basically together, or functions of t. That actually describes our stretching or our deformation of this path. This is the actual variation. We are going to call it delta q.
Before we move on, I just want to recap what happened. When we calculated the derivative of a function, the way we did that was take a small step in the x direction and look at the resulting change in the y direction. This is basically the exact same thing. We have a functional, and let's say the point we're looking at is q of x. So we take a small change in the functional, which is just a slightly different function. The change in the functional is another function, delta q of x. Since we want the endpoints of the similar function to be the same, the endpoints of delta q of x at point t1 and t2 have to be equal to 0. This is the exact same thing we did when we were taking the regular derivative. Now back to Jens to continue the proof.
With that out of the way, I want you guys to notice something. Delta q is yet again a function with respect to t. Okay, and if we were to differentiate both sides here, this side and this side, okay, we are going to give this thing a new name, q hat for example. If you've ever done inverse problems, you might know that we are going to call a minimizer of a function hat something, x hat, q hat. If we were to differentiate this thing with respect to time, okay, this is just going to give us q hat dot. And if we were to differentiate this left hand side here, or this upper side, well, what are we going to get? This is just the addition of things. We are going to use the linearity of the differential operator, meaning this is q dot plus s is just a constant, okay, it's going to stay where it is, and delta q dot, okay? Q dot plus s delta q dot. This is the differential of this thing. There was already some very important input. What other things could we say about this thing? Well, when would our curve, our new path be equal to our old path? So here's the question, when is q actually equal to our q hat? When are we going to minimize this function exactly? Well, when our degree of variation is going to go to 0. So for s going to 0, we have the case that our q hat is simply our q yet again. We are optimizing our curve this way, minimizing it in some way. Also, we would like to add some boundary conditions. I want you guys to notice that the closer we get on this new path to our nodes, the closer it also gets to our original path that we have here. Our arrow gets smaller and smaller. Our variation becomes 0 there. This term, our arrow that we are having, our noise in this function, is going to go to 0. So we are also going to have the condition that our variation at the endpoints is actually equal to 0. Okay, we do not have any variation anymore at our nodes. Now, all the basically hard work is already done, and now we are going to do some playing around. We are going to do the transformation we did here on this integral. Meaning overall, we are going to do the transformation where q goes to our variation path that we are having. So I of q plus s delta q is thus equal to, well, all of this stuff plugged into here. Our path is still the same. Integral from t1 to t2. Of our Lagrangian, this is what you would call in physics a Lagrangian, and then t, comma, q hat, comma, q hat dot. Like I said before, differentiating this thing is only like piecewise differentiation, and not piecewise differentiation, but we are differentiating each and every part in here, okay? Now, this is what we have at the moment. Let us think again when our path is going to be minimized. If you take a look at regular calculus, we know that if we take the first derivative of something and this is equal to 0, we know that there's a maximum or a minimum in some way. We're going to go by the same means here. We would like to differentiate this function and see when it's exactly equal to 0. Okay? This means that our path is going to be minimized, meaning it's equal to our original path basically. we would like to differentiate this, but with respect to what? Now, we just need to take a look at the variables. If it were dependent on q or delta q, then this wouldn't make any sense, because we are integrating with respect to t. Q hat and q hat dot are also functions with respect to t, so integrating those is just going to result in some constants. So the only parameterization that we have in here is with respect to s, meaning we could differentiate this thing with respect to s and see when it's going to be minimized. This also makes sense when you take a look at this condition. When s goes to 0, our function is going to be minimized yet again. Q hat is equal to q. Meaning overall, we are going to take d I q hat, I'm going to call it q hat, ds is equal to, well, the differential of this integral. The up and lower bounds are not dependent on s here, not dependent on the degree of variation, meaning we can make use of the special case of the Leibniz rule. If you don't know what it is, take a look into the description. If our function in here is nice enough, we can actually interchange this limit, so the differential operator, and this limit, our integral, and turn it into a partial derivative in here, okay? If you don't know what it is, just take a look at some of my videos or the explanatory video on the Leibniz rule for integration. So this is actually the integral from t1 to t2 of del s, so the partial derivative in s, of our Lagrangian that we have t, q hat, comma, q hat dot, integrated with respect to t. And now we can start to differentiate this thing. Now you might ask yourself, how could we differentiate a multivariable function? Let us take a look at a function in two variables, okay, and how we could differentiate it with respect to x, for example. So let us take a look at del t, or we are going to differentiate it with respect to t, of f x, y, where x and y are also dependent on t. This is just the chain rule, okay? Maybe you know it in one dimension. There's a generalization for n dimensions. We only need two dimensions here though, because we only have those two variables, q hat and q hat dot, being dependent on s actually. Meaning overall, if we were to use the chain rule, we are going to end up with the derivative of our f in x times the derivative of x in t, plus the same thing just with a y substituted into here instead of an x. Del y f del y t. Now we are going to apply this exact method to our Lagrangian that we have here. Meaning our integral is going to stay where it is. So the integral from t1 to t2 of this first variable in here, t, is not dependent on s, meaning we can just throw it out of the window, let it die in Mexico somewhere, getting eaten by hyenas. Now we are going to differentiate at first our Lagrangian with respect to the first variable, q hat. And then we are going to multiply it by the differential of q hat in t. Okay, it's as easy as it is. Plus, okay, next up is our differential of the Lagrangian in q hat dot. That's kind of a variable mess that we have right here. Del q hat dot dt. Okay. That's a lot of stuff we had to write out here. It's a lot of thinking we have to do, okay? Just bear with me for a minute longer, we are basically already done. Now we can actually simplify some more stuff here. If we were to take a look at the differentials of our, oh no, we are going to differentiate with respect to s here. I'm terribly sorry. Totally messed it up because of the rule that we have right here. Mistakes happen. Now we can totally simplify some more stuff here. If we were to differentiate our q hat with respect to s, this means that we are just going to end up with the variation in q here. So delta q. Same spiel goes for this part. We are going to end up with the variation in q dot. Okay, basically doesn't that cancel out? And all that's really left is to kind of evaluate this integral. Also, do not forget that we have boundary conditions later that are going to minimize our differential, our function in itself, our I, leaving us with the optimized function up here. Now we would like to do some integration by parts on this part right here. Simply because we are differentiating with respect to a time derivative, and we can actually make stuff a bit easier because we are integrating over dt. Okay, so let us just take a look at integration by part for this last part. We need something to differentiate and something to integrate. Plus minus. What are we going to integrate? Well, That's the only thing that we can really integrate because it leaves us just with the variation in q. Okay, so variation q dot integrated is just the variation in q. Now for the differential, we are just going to differentiate this part. Okay, so this is del q hat dot of the Lagrangian. It's nothing but we don't know, it's the time derivative. If this thing is differentiable, then yeah, let's go ahead and differentiate it. ddt of del q hat dot of the Lagrangian. And now simple integration by parts, meaning overall our I prime basically that we are having is nothing but we're going to have this first part here, so that's the integral from t1 to t2 of our variation delta q times the differential in q hat of the Lagrangian plus, next up is, this is the part that we are going to do integration by parts on. I'm going to close this up. Now integration by parts tells us that we are going to multiply those two together and evaluate it at the boundary conditions. Meaning we are going to have our variation times del q hat dot Lagrangian minus those multiplied together but with an integral around it. Okay? Simple integration by parts. Now we are going to have our variation in q d dt del q hat dot Lagrangian integrate with respect to t. Like I said, by applying the boundary conditions, we can actually solve this integration by parts problem. Because if you take a look, our variation vanishes at the nodes. This is what we have seen before, because it becomes arbitrarily close to our original curve. Meaning overall, both parts are 0. This is going to vanish. We are going to make use of the linearity of the integral to bring those two together. Okay, just adding the integrals together into one integral. Also, we have the very same variation here as a common factor. Meaning overall, I prime is thus the integral from t1 to t2 of variation in q and then del q hat Lagrangian minus ddt. I'm going to close this off. ddt del q hat dot Lagrangian integrate with respect to t. One last thing. We are seeking a minimization of this function here. Do not forget when this is going to happen. Exactly when we differentiate this and this is equal to 0. When it's going to be equal to 0 is exactly when we apply our boundary condition here, s going to 0. This is when we are going to minimize our function exactly. Meaning overall, I prime at s being equal to 0 is nothing but 0. We are going to plug s being equal to 0 into here also. This part is not going to change overall, but here on q hat and q hat dot something is going to change. If we let s go to 0, this is just going to be q and q dot. This is just what we were seeking. Meaning overall, this is the integral from t1 to t2 of our variation times del q Lagrangian minus d dt del q dot Lagrangian integrate with respect to t. And here's one last thing. When is a definite integral equal to 0? Exactly when the argument is equal to 0. The argument is a multiplication of two things. We don't want our variation to be equal to 0, okay? It's just something that does stretch our function in some way. We don't want it to be equal to 0. This is what I said at the beginning. Meaning overall, in order for this product to be equal to 0, we want this to be equal to 0. And this, what we have in here, are the Euler-Lagrange equations, one of the most important partial differential equations there actually are. I hope you did enjoy this little part. Terribly sorry for stuttering a little bit, and now back to Vivek for some applications. Ciao.
This is the famous Euler-Lagrange equation. Like Jens said, it's one of the key differential equations that has its applications in a lot of areas, like physics, chemistry, and etc. Let's revisit the distance functional we talked about and try to solve it using the Euler-Lagrange equation. So this is the distance functional written out before. So our Lagrangian is equal to the function we are integrating. Now let's write out the Euler-Lagrange equation. Let's look at each of the terms one by one. Since the function doesn't have a y of x term, the partial derivative with respect to y of x is just 0. Let's look at the other term. I'm gonna plug this term into Wolfram alpha to save us some computation. After doing that, we get this fraction, which we can set the numerator equal to 0. This leaves us with f double prime of x is equal to 0, and we can get the solution to this differential equation by just integrating both sides twice. This leaves us with f of x is equal to c0 plus c1x, which is the equation for a line. And so the Euler-Lagrange equation shows us that the function that gives us the shortest distance between 2 points is a line, which makes sense. Before this video ends, I want to thank Flammable Maths again for working on this video with me. If you haven't checked out his videos, I highly recommend you do so. Thanks for watching.